So, are you ready? Okay, my name is Ralf Klessen, and I will be talking about the very small-scale physics. So, I usually work on star formation, ISM dynamics, and this is also what I will be discussing in my lectures. I would like to start by motivating what are the physical processes that we must consider in order to understand the dynamics of the interstellar medium and in order to understand its ability to convert, at least in parts, into stars. And you see a few pictures that go from very small scales. This is from a calculation where we look at magnetic field amplification in a primordial halo. This is an observation of a protoplanetary disk in the Orion Nebula cluster. This is a calculation of a young stellar cluster which is completely dominated by collisions. This is NGC 3603, a very massive cluster, I think in the Magellanic Clouds, and you see again that stellar feedback affects the ambient cloud environment. The next one is a H1 image, so atomic hydrogen, the 21 centimeter of some galaxy from the SYNC survey. And again, in order to understand this object, we need to understand how the 21 centimeter emission has been created, how the radiation has been traveled through us, and eventually how it has been detected in our telescopes. And on the very right-hand side, let's see whether I can operate this thing. This one is a primordial halo, and instead of showing you the dark matter, I show you the gas as it flows into this halo and heats up and exhibits very complex dynamical structure. So these are, in a nutshell, the physical processes I would like to discuss in the course of this lecture. So I should thank the organizers for inviting me, but I think even more I need to thank a number of people who are involved in what I will be talking about. These clearly are people in the group in Heidelberg, but there are many other collaborators. I should also start with a disclaimer because I will be talking about stuff that is most dear to my heart, and as you might see, and as you might already know, in the star formation and ISM dynamics community, there are different schools that have highly disparate opinions about certain issues. So I try to be as objective as possible, but you should keep in mind that it's me who gives you this lecture and that my point of view will be biased towards a more dynamical point of view. And if you look at what used to be called the classic theory of star formation, which was more or less a quasi-static theory based on magnetic fields and magnetic field evolution, you will see that my point of view differs enormously. So again, keep in mind that it's me who gives you this lecture and that necessarily my point is biased to some degree. And I think that's extremely important in science, that you always understand who is giving you a lecture, who is giving you a talk, because he or she will always come with a whole slew of history, educational history, and history of thinking. And I think this explains many of the biases we see at conferences in schools. So keep this in mind. So the structure, my structure is a bit more mixed because I would like to put lots of emphasis on the physics. And in this first lecture, I will not talk about numerics at all. I want to give you a motivation. Oh, these two, I see. I want to give you a motivation why I think we need, in a modern theory of ISM dynamics and star formation, need to take essentially all the relevant physical processes into account. That it is not, as people have attempted in the past, possible to just focus on a few aspects. That may be possible in a few selected and specific cases, but if you want to understand the overall dynamics, and if you want to integrate that, let's say, into galaxy formation and galaxy evolution, if you want to combine the small and the large scales, you are bound to think about multi-scale and multi-physics processes and modeling approaches. So this is what I would like to motivate in this short introduction. Then I want to talk about ISM dynamics and star formation. This may change a bit. Then in the second part, I want to zoom in into smaller and smaller scales and talk about the star formation process. And at the very end, I would like to give you a few selected examples ranging from star formation in the primordial universe. I want to do a short excursion on dark stars, which have been proposed to be driven by the annihilation of dark matter, so a very cool physical experiment or thought experiment. And I want to talk a bit about magnetic field amplification. So before I start, I think it is important to introduce some of the relevant books. This is an overview of which I think are very good books in ISM dynamics and star formation. Can you still hear me? So I brought a few, and in the break I leave them here. You can have a look. Here's also a more proper overview where you can find them and who are the authors. There's also additional literature. There are reviews in the astronomy and annual reviews of astronomy and astrophysics or reviews of modern physics, etc., that cover various aspects of ISM dynamics and star formation. And again, I keep this list here and you will have access to the PDFs. As you shall see, I will also talk about physical processes. In particular, I want to say a few words on modeling radiative transfer, and I will be using in my hands-on session examples that have been designed by Kees Dullemont using his Monte Carlo-based radiation transfer code. So the idea is that in the hands-on tutorial on Friday, you try to model the spectral energy distribution of a star, main sequence star, I think 2 solar masses, that is embedded into a cloud that is composed of dust and carbon monoxide. And you should calculate what is the lines you see, what is the temperature distribution, etc. Because this is the stuff that you observe if you were an observer that looks at, let's say, infrared submillimeter emission. There's also, I think, quite cool, a list of molecules with detailed descriptions on the internet. And by now there are at least 100 plus molecules identified, and it's growing almost every day. And these molecular line databases, like the one in Leiden, are essential laboratory groundwork that is needed to do things like chemistry or line transfer calculations. So, why is that important? Let me start with my short introduction, and let me start with a bit of phenomenology. So, this is the most expensive picture ever taken. I would say people have taken the Hubble Space Telescope, tried to figure out somewhere in the galaxy a window where there are no foreground stars, and just exposed for almost 2 weeks. And out of nothingness, suddenly you see something like 10,000 galaxies. Let me switch it. Okay. So maybe it's better now. So what you see here is galaxies, but the light from these galaxies is starlight. And as you have seen from Volker's lecture, the more redshifted the stuff is that you see, the more distant in the past this light has been emitted. So you want to look at infrared wavelengths, and if you focus on this little spot, this is one of the most redshifted objects in this sample. So if we worry about ISM dynamics and star formation, we can say that basically as soon as the conditions in the universe were right, stars have been forming. And this is our main source of information we have of the local and also the distant universe. So in order to understand that better, I think we need to go to more nearby galaxies, because then we see the correlation of the large and the small scales. This is M51. And you see a beautiful large-scale spiral pattern that has been created by the perturbation due to this satellite galaxy. But if we zoom into smaller and smaller scales, we see that young stars form typically associated with these spiral patterns. You see these kind of, what is this, pink-colored emission. This is the H2 regions that are created by very massive stars. Stars, per definition, massive stars per definition have very short lifetimes. So you look at recent star formation events. And you see a correlation between the large-scale pattern here. This is something like, what is it, 100 kiloparsec across, maybe less, and the actual size scale of stellar birth, where you need to accumulate material worth, let's say, a cubic parsec. So 10 to the 5 orders of magnitude, no, 10 to the 5 in difference in scale. So if we then look to different types of gas, we shall see that we classify the interstellar medium by the chemical state of its main constituent, hydrogen. We classify it into atomic hydrogen, molecular hydrogen, and in the vicinity of a hot star, ionized hydrogen. So if you look at the emission of the atomic hydrogen, we see it is very extended, yet there are correlation with spiral arms. But if you look at the molecular hydrogen, we see it is much more, let's say, focused towards the center and towards spiral arms. And if you look at the star formation tracer, we see that there is a good correlation between the molecular gas and the star formation, but not such a good correlation between the atomic hydrogen and star formation, or the atomic hydrogen and molecular hydrogen. It rather looks like where we have most of the molecular hydrogen, we have a deficit of atomic hydrogen. So we need to understand how we can transform the different phases, atomic, molecular, ionized, into each other, and how this relates to the star formation process. And one of the first disclaimer I think one needs to say is, or one of the first hints towards a discrepancy or a debate in the current literature is whether you need molecular hydrogen to form stars, or whether molecular hydrogen is a mere tracer of star formation. It happens to be that when you are dense enough and well shielded enough to have stars, or to have gas that goes through this phase in order to form stars, at very high densities, you also form molecular hydrogen along the way. And I would argue it's the latter, but there is a debate. This is in the domain that Nick will be speaking about. We can see that there is a good correlation between the density of star formation, so this is the star formation rate per kiloparsec square, and this is the gas density, solar masses per parsec square, and you can see there is a correlation. However, there are different regimes. At low densities or column densities, it is dominated by atomic hydrogen. At large densities, it is dominated by molecular hydrogen. There seems to be different relations, and in a starburst regime, there seems to be yet again a different relation. Is this really true? Or is this, let's say, a fluke of not understanding the relation between tracer molecules and the bulk of the mass? That is, again, a debate in the current literature. So let me then zoom into yet smaller scales. Let's go to our Milky Way. This is the emission of carbon monoxide. I will argue probably tomorrow and the day after tomorrow that molecular hydrogen, the dense and cold phase itself, does not emit radiation because it's a symmetric molecule, so it has only forbidden electrodipole. No, it has no electrodipole emission, it only has a quadrupole emission. So very weak emission, and instead you need to go to very strongly polar molecules like CO that can emit very strong rotational or vibrational lines. So what you see here is a survey made by the CFA guys of the galactic plane, and you see various structures here. Let me focus here on the Orion A and B cloud. These are the two clouds, and just look at these scales here. The full moon would be roughly the size of this dot here. This is the entire constellation of Orion. So these are huge entities on the sky. If we had radio eyes, not only could we easily listen to the radio or watch radio, the sky would look extremely different. So this is more or less an optical emission with some infrared parts. And let us zoom into the middle star around the sword of the Orion warrior. Here's the belt, the feet, the hand, etc. And what you see here is the Orion Nebula cluster. This is an infrared image because there is some veiling in front of it, so you need to go to slightly longer wavelengths in order to see something. And you see a cluster of very young stars. And from looking at such a region, we see that stars typically do not form in isolation. Rather, they form in clusters and groups and associations. Second, they form in the molecular gas. And you can see that because third, this is strongly influenced by feedback from the most massive star. So Theta 1c Orionis produces a copious amount of UV photons that are capable of ionizing atomic hydrogen and dissociating molecular hydrogen. And the bluish stuff is the recombination you see as this ionization front eats itself, here we go, into the background molecular cloud. And if you look very closely up here, you see the Beckley-Neugebauer object, where star formation, massive star formation, takes place right now. These stars here are roughly 1 million years old. This stuff here is in the main accretion phase. It takes something like, let's say, 500,000 years, a few 100,000 years to form a star. Let us zoom into the central part. This is the so-called trapezium of the Orion Nebula cluster with Theta 1c Orionis. And you see that the star interacts with neighboring features. So you see these drop-shaped structures, and if you look more closely, you see these are protoplanetary disks, so-called proplets. So these are dusty disks that you see as shading silhouette in front of this illuminated background. And what happens now is that not only this star emits UV radiation, it also emits a very strong wind. The UV radiation hits this disk, the disk evaporates material, you have an evaporation flow off this disk. This is hit by the wind emitted from the star, and you have a shock. So we need to talk about radiative shocks. I will argue later on that there are also magnetic fields in such regions. So very complex physics. And of course, the wind from the massive star wins against the wimpy wind coming from the evaporating disk and forms this droplet shape. And here you see where the two shocks or the two fronts meet, you have a strong shock feature. If we zoom in at smaller scales, we see that, again, stars do form in clusters, but typically stars do form as binary systems or higher order triple systems. So while it is indeed true that most low-mass stars are isolated stars, our sun is kind of an exception. It is in the range where most stars are in binaries. If you look for very high-mass stars, you see that the binary fraction is actually much larger than unity. It's typically 2, even 3. So how can it be larger? If you count a triple system as 3 or a quadruple system as 4, then you see that many of these objects are quadruple or triple system, essentially all of the trapezium stars. And I would argue later on that it's easy with simple statistics, or complex statistics, to make predictions of the initial mass function. It is extremely difficult to make proper predictions about the binary fraction of stars. And eventually, the radiative feedback blows away the gas, and we see a young star cluster, well, not so young, these are the Pleiades at 100 million years, that is revealed. It's an open cluster that eventually dissolves over giga-years timescale and populates the galactic field. So this is, in a nutshell, the phenomenology that we as star formation or ISM dynamics theorists need to explain. Now, this is a school on theory and on numerics. So how do we approach that problem? I think the first thing to notice is we need to cover enormous scales, right? We go from 100 kiloparsec galactic scales down to star clusters a few parsecs across, a few thousand AUs across, a stellar radius, an Earth-like radius. So the only force that can cover all these scales is gravity. It's the only fundamental force that is not balanced on large scales. So the weak and the strong forces are very short range. The only other long range force, the electromagnetic or electric force, is balanced because you have two different charges that can compensate. But gravity only has one charge, if you wish. It's always attractive. So it's the only one, the weakest one, that is not balanced. So it is clear that in order to cover these scales, and in terms of density, the typical density of the interstellar material is 1 particle per cubic centimeter, maybe a few particles on average. If you compare that to the 10 to the 19 particles per cubic centimeters that you breathe in and out every moment, or the, I don't know, again, factor of millions higher density in the interior of the sun, then you see, again, you need gravitational compression to cover these forces. So we have identified one force that we need to take into account. Now, what are the other forces? The other forces are opposing forces. So gas pressure, for instance, does not want gas to be compressed. If you compress gas, usually the temperature goes up, pressure arises, and you have an opposing force. We shall see that you can overcome that by resorting to internal degrees of freedom. You can excite radiative transitions that carry away this energy. And under many circumstances in the interstellar medium, if you compress the gas, it will actually cool. That's a major driver of ISM dynamics. And we need to understand that. It involves radiative transfer. It involves microphysics, the chemistry of these cooling processes, the coupling between radiation and matter and different phases of matter. I also want to argue that there is a high degree of turbulence, and that is an important agent that can resist gravitational compression on large scales, but it can also trigger collapse on very small scales. A classic opposing agent was magnetic fields. Magnetic fields do not want to be bent, they do not want to be compressed, and the energy density is appreciable. So this needs to be taken into account. And clearly, if you look at a region like that, radiation pressure, so the interaction of photon, the absorption of photon on dust, say, or line-driven winds on lines, can add additional pressure, and here it's strong enough to create this large cavity. What I would like to argue in the course is that it's not enough to just focus on the interaction of this and this, or this and this, or this and that one. No, I think in a modern star formation theory, all of these processes need to be taken into account. That makes it a very hard problem. In order to understand the current status, I think it is good to make a short historic digression. So let me try to give you a short historic overview of the evolution of star formation models. And in order to do that, we go back a bit more than 100 years to Sir James Jeans. And what he did is he said, oh, I have a self-gravitating object, and I look at the effects of gas pressure. So I have gravitational gradients, I have pressure gradients. Under what circumstances do they compensate? Is there a critical mass? So what you do is, what you have studied at length in your education, you try to find the equilibrium system. In this case, it's a homogeneous density. You put in a small fluctuation in density, and you see how it evolves by looking at the linear stability analysis. So you formulate the equations, continuity, Euler's equation plus Poisson's equation. You combine it in such a way that you get a wave-like equation. You study that in Fourier space, and you get a dispersion relation that relates the frequency with the wave number. And this is what happens here. If you neglect the source term on this side, you see it's simply the dispersion relation of a sound wave. However, self-gravity adds a source term to the problem, and it turns out that if this term dominates, this goes negative, and we have exponentially growing or decaying modes. Instability means exponentially growing modes. You can then cast it into a critical wave number, or if you say I have a cubic perturbation or a spherical perturbation into a critical mass. Oh, and this is wrong, this must be plus. And you see this critical mass, named Jeans mass in honor of this guy here, scales inversely proportional to the square root of the density and to the temperature plus 3/2 power. So larger temperature, more pressure, more resistance, collapse, higher density, more self-gravity, easy to go into collapse. Now, if you plug in the numbers, take a interstellar gas like 10 to the 5 solar masses, temperatures of 20 Kelvin, you see that this Jeans mass is of order of a few solar masses. That means the interstellar gas class is thermally highly unstable, and you should have converted all the gas in the galaxy into stars a long time ago. Clearly, this has not happened, so people have desperately been trying to find ways to stabilize this gas. And it was then Chandrasekhar and von Weizsäcker who said, but let's now assume we have turbulence, right? Turbulence are random motions on particular scales. Let's assume we have microturbulence, so we can separate the scales where our turbulence sits from the large-scale dynamical scales. If the turbulence sits on very small scales, I can safely add it to the sound, to the thermal velocity dispersion, and I get an effective sound speed, an effective thermal velocity. So this is this equation. And if turbulence dominates, I can just have an effective, very high temperature. I can stabilize my medium. This is a cool idea. However, there are two problems. First of all, the microphone has problems. Second, the velocity dispersion depends on scales. And if you do a scale decomposition, you see that most of the energy is carried on the largest scales. So the microturbulent approach is not valid. Third, then, in this new counting, we have supersonic turbulence. And I will argue in a minute that the fact that we have shocks that can compress gas can lead to triggering star formation. So this simple approach has problems. And note that it is still in the literature quite a bit. So it was then in the 50s and 60s that people like Lyman Spitzer said, but wait a minute, the interstellar medium is magnetized. And at that time it was thought that the energy density in the magnetic field is at least comparable to the gravitational energy density and exceeds the thermal energy density by a bit. So if you make the same Jeans analysis, but now you have a homogeneous magnetic field, you notice field lines do not want to be compressed, they do not want to be bent, and you come up with a critical mass to flux ratio. So you can count the number of field lines that go through a spherical blob of gas, and if this number of field line is larger than a certain value, well, here it is, this thing, with G being the gravitational constant, and this is all in CGS units, where the magnetic field and the electric field has these strange units, then you see that the field can oppose collapse. Now, you had the opposite problem, because now you should not form any stars at all. It was then Frank Schuh who came up with the idea, but wait a minute. What Spitzer and others did, they have assumed ideal magnetohydrodynamics. But in reality, we have only partially ionized plasma in the interstellar gas, right? We have ionization degrees, let's say 10 to the minus 6, 10 to the minus 7. The bulk of the mass is in the neutral. And while only the ions and electrons cling onto the field lines, gyrate around the field lines, the neutrals have no idea that there is a magnetic field. They only know about the field by colliding with the ions and the electrons. Now, if we have not enough ions and electrons, there will be a drift. The neutrals will drift through the field lines and accumulate and eventually exceed the critical mass to flux ratio. Then in this particular theory, suddenly the field was gone, and you can make a very simple, beautiful analytic theory of how star formation should progress. It makes certain predictions, namely that collapse should start from a singular isothermal sphere. Density falls off is 1 over r squared. It has no velocities initially, and this gives you a mass accretion rate that is constant and only depends on the sound speed, so the temperature, and the the gravitational constant. Note that this value that you see always in the literature is only true for having initially 1 Jeans mass. If you start with a blob of gas that is worth 3 Jeans masses or 30 Jeans masses, this rises rapidly to much higher accretion rates. So that is a caveat or a feature of this so-called standard theory of star formation that is often neglected. So this value of roughly 1 c squared cube over g is only valid if you have 1 Jeans mass initially. Now, this, I think, for a long time dominated star formation theory, but it has problems. No one has ever seen a singular isothermal sphere. It predicts no binary stars. You see that the accretion rates are usually larger. You see that the infall rates extend to larger radius, etc., etc. In particular, it turns out that the magnetic field may not be so strong as it has previously been assumed. What is plotted here is the line of sight magnetic field from Zeeman measurements. Again, you see in order to interpret these observations, you must know how the Zeeman splitting comes into being, how these lines are transported to you, and how this can be interpreted then in a model of the blob of gas that is threaded by magnetic field lines. So in order to say, oh, this corresponds to critical mass to flux ratio of 1, needs many, many steps in between that I think we must understand in order to really appreciate what this means. So anyway, most of these measurements say that the magnetic field is too weak to stabilize such a core. In addition, it turns out that the magnetic field do not prevent the decay of turbulence. If you do linear theory, so you have Alfvén waves that going back and forth through a medium, they do not dissipate. So it was thought the presence of a magnetic field prevents the decay of turbulence. And we know that turbulence decays rapidly in the hydrodynamic case, and it was only shown, let's say, 10 years ago, well, 15 years ago by now, that it also decays in the magnetohydrodynamic case. So only when you go to second order perturbation theory, you see that the waves can interact in a nonlinear fashion and dissipate the energy. So again, quite recent developments. If you look at the structure of the field lines, again, you don't see the field at all. You need to infer it very indirectly from, let's say, Zeeman measurements or dust polarization. But sometimes you see at least the polarity of the field along the line of sight. And this is what Dick Crutcher has done a few years ago. And you notice that this has a plus sign, this is a minus sign, a minus, and a plus. So across these protostellar object core, there are field reversals. The magnetic field goes in this direction, then it turns around, it goes in this direction. So it has a very complex morphology. This again is incompatible with a theory where magnetic fields dominate the energy density, because then they would straighten out more or less, and the gas density would follow the magnetic field. Again, this has triggered a fierce debate in the community, and this debate is not over yet. Good. Let me then come to my favorite model. It's what I call the graviturbulent star formation theory, and the idea is to revisit again turbulence. But now, in a sense, do it right and take into account that it is in the supersonic regime, at least on large scales, and that it is threading throughout all the scales of the interstellar medium. So the statement is it plays a dual role. On large scale, just like the microturbulent, it can provide support. On small scales, it can trigger collapse. It is in line with the dynamical, with the short dynamical star formation timescale that we see in young clusters. It can explain high binary fractions, the complex spatial structure of embedded star clusters, etc., etc. So how does it work? The idea is we have on large scales, let's say atomic gas. This is what Nick will be talking about in great detail. You have fluctuations. I do not specify where they come from, what drives the turbulence. Some of these fluctuations are dense enough that you can quickly go into a chemical phase transition and turn the atomic gas into molecules. Now you have additional cooling channels. And again, whether you need these additional cooling channels or not is a debate. And you see then a transition to molecular gas. Inside the molecular gas, the very process that has accumulated the gas in the first place, that has shuffled gas together to make the density higher, drives internal turbulence. So I think accretion-driven turbulence is a universal process that can explain the velocity dispersion on galactic scales inside molecular clouds and on scales of molecular cloud cores. So this turbulence now, because we are talking about very cold gas, is now in a highly supersonic regime. It triggers huge density fluctuations. Some of these density fluctuations can become gravitationally unstable, collapse, and form individual stars or binary stars. So I would argue that it is the turbulence that triggers the fluctuation spectrum, and gravity then selects certain fluctuations to go into collapse. So I will talk about turbulence and its statistical features probably on Wednesday. Right now, let me just tell you that you can characterize turbulence by this typical slope that you have here. The idea is you drive the turbulence on some large scales, energy dissipates on some small scales. This needs to be debated, what drives this turbulence. This is probably some ambipolar diffusion type process, and in between you have what is called the inertial range, where simply large eddies break into smaller eddies and yet smaller eddies, and eventually the eddies are so small that they have the size of the mean free path, and this is just heat, thermal motion. If we have incompressible turbulence, then this slope is well defined. It is the Kolmogorov slope of -5/3. If we talk about shock-dominated turbulence, Berger's turbulence, then it's simply the Fourier transform of a shock. It has -2. Notice that between -5/3 and -2 there is very little difference. So it is difficult to distinguish just from looking at the power spectrum what type of turbulence we have in the interstellar medium. Typically the slope is somewhere in between -1.8-ish. So the scale separation depends on the Reynolds number. So the Reynolds number on each scale gives you the ratio of the advective terms and the dissipative terms. I come to that soon. More important is, if you come back to this turbulent cascade, that we need to distinguish different scales. There is here a scale where the turbulence is supersonic, and here a scale where it is subsonic. So here it can trigger further star formation. Here it is simply thermal motion or thermal type motion. There is somewhere a scale where this hits the turbulent cascade. So scales here on the right-hand side are in the subsonic regime, pre-protostellar course, and here we are in the supersonic regime. And it is a useful exercise to place typical structures on this diagram. So if you look at molecular clouds, so here large scales, I plot here the wave number, large scales, small scales, are typically vastly in this supersonic regime. So supersonic turbulence creates the complex density structure we observe in these objects. if you go to smaller scales, cluster-forming cores, like blobs of gas that would form the Orion Nebula cluster I've shown you before, they are still in the supersonic regime, but they are getting closer to the sonic transition point. And if you go to individual prestellar cores, there's a transition to coherence, transition to being dominated by thermal pressure. These are the guys that form individual stars or binaries. So we've seen that. Let us now fill that with life. Let us look at the Rho of Juchus cloud, and let us focus at one of these blobs that we observe here. So the idea is, on such a scale, we still are in the slightly supersonic regime. Let's say Mach numbers of 5-ish. We know if we have isothermal turbulence, that this is basic hydrodynamics, that the density excursion scales with the Mach number squared. So you get on these scales density fluctuations of order of 25. So strongly nonlinear. Much away from the initial conditions the universe evolved away. So the idea is that there are these blobs of density fluctuations, and the question is, some of them may go into collapse, some may simply dissipate again. And indeed, we observe young stars and their outflows in such a region, and the idea is now that you have the convergent flow that creates these blobs of gas, and if the mass exceeds the critical mass, it goes into collapse. If this is not the case, it expands again after this convergent flow has ceased to exist. And this gives you typical timescales, and indeed, many of the blobs people identify in nearby molecular clouds are in the unstable in the stable regime and should, if Ram pressure goes away, re-expand again. So it's a continuous coming and going of structures. So if you take one snapshot, you could say, well, maybe it is a representative snapshot. But you need to keep in mind that many of the theories of star formation based simply on this turbulence picture take one snapshot and evolve it forward in time. And forget about this continuous formation and dissipation of these objects. Good. Now, in order to form a cluster, you must have a region that as a whole is genes unstable, contracts as a whole, and then we look at the individual fluctuations. So this is a situation where turbulence may decay on relatively large scale. This would form a cluster. If, however, turbulence dominates the energy budget, this would disperse and you typically form only a few objects with very strange IMF. So let us focus on the second case. Let us continue this cartoon picture and say turbulence decays, the entire thing contracts. However, the densities in these blobs of gas is larger. The freefall timescale is proportional to the square root of the density. So the higher the density, the shorter the freefall timescale. So these guys will run away the global collapse. Typically in the center, where you have the biggest and densest blob of gas, star formation sets in. First, you form a protostar, and material accretes onto this object. Maybe more form, and you can speculate now, what does it mean that you now have these in a cluster type environment? We could say, well, now we have protostars that do accrete gas from a common reservoir of material. And now collisional dynamics becomes important. Exactly what Volker tried to avoid for the dark matter is important in this case. You form a triple system which is unstable and typically kicks out the lowest mass object. And it is clear that this will influence the mass accretion rate and the IMF. Eventually, the most massive star in the center becomes more massive than 10 solar masses. It enters the main sequence and produces UV photons, and it creates an ionized bubble that terminates subsequent star formation here. And this is a situation like, oh, it was not 3803, it is 6002 that I have shown you before. And then you have a situation like that where you have something like 10, 20 O stars and a whole cluster of small objects. Now, this was a model where gas physics was very simple, isothermal, and we looked at the interplay of turbulence and self-gravity. Now, of course, the kinetic energy in the turbulence, the potential energy and the magnetic energy are roughly equal. So I made a mistake. So typically models based on hydrodynamic turbulence are too fast. They form stars too quickly. The dynamics is too violent, if you want. So star clusters do form, but more slowly. And it turns out that the initial conditions do matter. And that brings us back to the numerics, because we all do that wrong. Unlike in cosmology, where we know the initial conditions very well, the initial conditions in star formation and ISM dynamics are not known very well. And the typical numerical simulation takes a blob of gas that comes out of nowhere, is worth, let's say, 1,000 solar masses, shakes it, and let it evolve. And there is hardly any calculation on the market now that takes the formation of this blob of gas into account. But this formation is important. And I want to argue that this is important towards the end of my lecture. So keep that in mind when you see these beautiful movies that are on the market and that I will show you. That typically the initial conditions are not right. And that is a critical issue that is often disregarded. So I think the current status is that we have a multi-phase and a multi-physics and a multi-scale problem. And all these processes I've shown you before need to take into account consistently. It depends on the environment which one dominates. If you zoom into a small, low-mass blob of gas that forms a single star, probably thermal physics and self-gravity and a bit of radiation is fine. If you talk about the cluster forming blob of gas, feedback becomes important once you form massive stars. Outflows are important. You need to connect it to the turbulent environment of the galaxy. Molecular cloud formation must be informed about the context, the general dynamics of the galaxy. I think we are now in a situation in this field where the small scale dynamics, the stuff that I do, and the intermediate scale dynamics and large scale dynamics that Nick or Volker are doing, that they meet. And I think that is the interesting part about such a school. We can discuss about the same scales. We can discuss about how we can use the information we gain from these observations and from small scale simulations. How we can use that to construct subgrid scale models for large scale dynamics. So I see that I'm also running out of time. I will end by showing you this beautiful image, which is from the Carina region. The very massive star Eta Carina is up here. Here's the cluster Trumpler 14, and you can see it's a mess. And this is what we need to understand, right? So this is a dusty, partially ionized plasma. So not only do we have gas, we have dust. Why do we have dust? Because we see this obscuration. This thing, for instance, here. It's full of dust that blocks the light from behind. Or here, these elephant trunks. We see these shock fronts. We see all kind of dynamical features here. Let us zoom into this region here. So the radiation and the winds from Trumpler 14, from this cluster, has blasted a hole in this molecular cloud environment. But where the density was larger, some regions have resisted that and have created these elephant trunks. So this is why you always have these kind of arm-like features in molecular clouds, in star-forming regions. Now, if you look at the very tip, what you see here is the presence of a young star. Why do I know it's a young star? Because there's a jet. So the accretion disk that forms around the young star is magnetized. It drives jets in the polar directions, up and below the disk. This can accelerate material that makes these bow shocks as the jet plunges into the ambient material. The jet has time structure you can see in these knots. There's another one. It is even more complex. Bow shock here, bow shock here. Notice that stuff here. Isn't that strange? evaporation seems to be in this direction. However, the radiation comes from up there, the 5th floor of this hotel. And yet, so it should be all dragged along here, yet it seems to evaporate in right angles. The only explanation I think I can come up with, or others, is there must be a magnetic field that is in this direction that forces the electrons and protons to gyrate around the field lines in this direction. So, in some sense, this is a very depressing image, because in order to really understand that and model that, we need to talk about non-ideal magnetohydrodynamics in dusty plasma. We need to talk about the coupling between radiation and the dust and the gas. In order to understand this image, we need to understand the transfer of the photons to us, to our detectors. We need to understand the complex dynamics that takes place here, the outflows and the winds, etc., etc. So, from a theoretical approach to study ISM dynamics and star formation, all that stuff needs to be included. So, magnetohydrodynamics, chemistry, radiation, stellar dynamics, stellar evolution, plus laboratory work. And I would like to stress that this is extremely important, because the rates that we feed into our chemical networks, the rate coefficients we use for the radiative transfer calculations, they all come from laboratory measurements. And often they're extremely unprecise. And it's just guesswork, right? 3-body H2 formation in the early universe, the rate is uncertain by a factor of 1,000. Which one is the right one? Does it change the picture if I pick the small one or the big one? These are all questions that need to be addressed. So this is, in some sense, Volker's domain. He will be talking about massive parallel codes, SPH approaches, grid-based approaches. He will talk about Arepo, but there are other ways to solve directly Boltzmann's equation. Chemistry, I will be speaking a bit of chemical networks. Also, Nick will be addressing the question of H2 formation. How then to treat with radiation, continuum versus lines, Monte Carlo methods, characteristic methods, so ray tracing methods, etc., etc. There's a whole slew of schemes which all have their pros and cons. I try to give you a short, very short overview. How to combine it with hydrodynamics, post-processing is not good enough. We need to combine it because it will influence the dynamics. Stellar dynamics, we have seen that in dense star clusters, stars, while accreting, do talk to each other. How do we deal with long-term integration in binary orbits is a challenge. Stellar evolution, in our star formation calculations, when we talk about feedback from massive stars, or also low mass stars, we need to take protostellar evolution into account, because this gives us the subgrid model for how many photons we need to shoot into our system. So this needs to be done, and that is, I think, just at the beginning of what happens in this community, and I think much more will happen here. So all of these needs to be connected and combined with laboratory work, and I should end here. So, and I take questions. Thanks for your attention. So that was brute force. I try to give you more details as we go along. This is just a motivation that we need to worry about this physics.
So we have time for only two questions.
If there are two questions.
So you said that it was debated the role that molecular cooling played in driving star formation. Could you say a little bit more about that?
Yes, I will say more about that, I think, in 2 days. So the question is, you need cooling in order to get rid of the compressional heating as you assemble the material. one of the strong cooling powers that is provided in the molecular phase comes from the rho vibrational transitions of carbon monoxide. So people have argued you need this cooling in order to get cold enough in order to form stars. Now, if you look at the cooling strengths provided by C+ and C1, it is within a factor of 2 equivalent to the molecular one. So if you take a chemical network and you switch off on purpose the formation of molecules and the cooling rates by molecules, you just delay collapse, but in the end you get more or less the same dynamical behavior as with the molecules. Now, of course, this is a completely artificial situation because in reality you have shielding, you do have the molecules. And eventually they take over the cooling by others. So what does it tell you? It tells you that you can form stars without molecules because you have other cooling challenges. However, as under normal circumstances in the, let's say, solar metallicity, LMC type metallicity environment, you always form these molecules as you go denser and denser and get better and better shielded. Only when you remove the dust and the shielding, if you go to extremely low metallicities, you can make stars without the molecules. And you can look at the star formation CO emission ratio, for instance, at present days and at high redshifts, and you see that this seems to support this trend. But again, there are different opinions on that. Nick, do you want to say something on that?
Well, not right now.
Okay. Yes, so Nick will also say something about it, and you will probably hear a slightly different opinion on that. Yes?
So you show the several different cores in the... Okay. So you show the core, several different cores in the molecular clouds, and then the star formation in each cores are related to each other, or they are the separate process?
Again, you are addressing a question that is debated in the community. So there are people who say, if I have a decomposition of molecular cloud structure, aka if I have a distribution of cores, I take each core and convert it into a star. I take an efficiency of 1/3, and then I can convert the core mass function that people observe into a IMF, the stellar mass function. This, I think, is too short-sighted because, for 3 reasons. If you look at many of the cores that are identified, they will never form stars because they're not Jeans unstable. Second, if you force them to form only one star, you tell, or you are saying that these typically have 1 Jeans mass. So the big blob of gas must have a lower density. Otherwise, it would have many, many Jeans masses. It would be vastly unstable and would fragment. So in order to prevent that, you must imply in your, from the core mass function to the IMF thoughts that these cores have 1 Jeans mass. We know the collapse time scale, the freefall time scales as the square root of the density. So these high mass blobs of gas take much longer to collapse than the low mass guys. Now, if you say I have a blob that is worth 100 solar masses, I have a blob that is worth 1 solar mass, you cycle 10 times through the 1 solar mass guys before the 100 solar mass guy goes into collapse. So that means if you say these follow a power law, the power law that comes out of that, if you take the subcycling into account, has a slope that is more shallow by +1. So if this is your assumption, you must not have the CMF being equal the IMF. Now, of course, you can say maybe it doesn't fragment. That is the way out. Still, you may have interactions and so on and so forth. So I think this is an interesting theory, and it's certainly a step in the right direction, but it's not all there is to form stars. Long answer to a short question.
Okay, thank you. I think we really need to stop now. We will have a 20-minute break, so let's be back at a 11:15. sharp, please. 11:15, we'll start again.